As we begin our unit on quadratics, we are looking at what do quadratic functions look like in graphical form, equation form, and table form. So in graphical form, the equation forms a curve known as a parabola. Okay? You'll often see the parabola open upside down, and there's even maybe more real-life applications. Think about a ball that goes up in the air and gravity takes over and it falls back down. In equation form, quadratics have a squared term. Here's an example of a quadratic. 5x squared minus 3x plus 3 equals 0 is a quadratic equation. And it's this x to the second power that makes it quadratic. So here's a fun fact. The name quadratic comes from quad, meaning square, because the variable gets squared. It's also called an equation of degree 2. So I always think, how hot is it? Well, it's like where the degree symbol is, because the highest exponent is 2. And there are quadratics that are sometimes in disguise, but we'll get to that in a second. So standard form of a quadratic looks like what you see on your screen here, where the variables are in order in decreasing degree. So x to the second, x to the first, and then this would be x to the 0 or no x at all. A, B, and C must be real numbers, and what else about A has to be true? Well, A could not be 0, because if A is equal to 0, then it's no longer quadratic. So here are a few examples. Let's identify the values of A, B, and C in each of these. And the first one's done for you, A being 2, B is 5, and C is 3. In the next one, the x squared term, A is 1, it's the coefficient in front of x squared, B is negative 3, keep your sign, and C is 0, there is no constant. In this last one, A is 0 because there is no x squared term, B is 5, and C is negative 3. So technically, this one is not a quadratic. This would be linear because the highest degree is 1. It would make a line. So you list two examples of quadratic equations, like x squared minus 5x plus 52 equals 0. And A, B, and C in my example would be 1, B is negative 5, and C is 52. You come up with your own. Some non-examples would be like x cubed plus 4x equals 0, because you have an x cubed term. That's what's wrong with this. The highest degree has to be 2. If I have x to the 4th plus x squared equals 3. Even though there's an x squared term, you can't have an x to the 4th for it to be a quadratic. So on the screen, there are several quadratic functions that don't readily maybe look like quadratic functions. So we're going to change each of these to standard form. Here's a reminder of what standard form looks like. It goes quadratic term, linear term because it's to the first power, and we call this one the constant term. So I'm going to just zoom in here on this first one, and we are going to change this to standard form. So I'm going to do that by subtracting x squared from both sides, and then I'm going to need to add 4x to both sides because my goal is to get 0 on the one side. So that would give me 0 here. And on this side, I'm going to combine my like terms. I'd have 2x squared. I'm going to put the 4x second and the minus 5 last. So in standard form, just going to rewrite this one more time. And I like my 0 on the right. So let's just quickly identify A, B, and C to make sure we got it. So my A is 2, B is 4, and my C is negative 5. Now I do want to point out that if you had taken everything over to the left side, what would have happened is every term would have had the opposite sign, meaning it would have been negative 2x squared minus 4x plus 5 equals 0. And that's completely acceptable. Just kind of the standard thing to do is we like what's called our leading coefficient, this first number, to be positive. Okay, so the one in red here is the more acceptable answer. All right, so let's go on to our second one. Our second one here, 2t times the quantity of t minus 4. Well, I'm going to begin by, I know I'm going to have to get everything combined, so I'm going to distribute. And when I do, that gives me 2t to the second minus 8t equals 10. So one more step, if I just subtract 10 from each side, that's going to result in 2t squared minus 8t minus 10 equals 0. And now, just for practice, I'm going to identify my values of a, b, and c. So a is 2, b is negative 8, and c is negative 10. All right, so now we have 0 equals 2 binomials. So what am I going to do? Well, I need to distribute. I need to multiply d by everything and then negative 5 by everything. So I'm going to have 0 equals 2d to the second power plus 4d, and now I'm going to distribute the negative 5. So that's minus 10d minus 20. And I've got some like terms here in the middle that I need to combine to get a final answer of 0 equals 2d squared minus 6d minus 20. So a is 2, b is negative 6, and c is negative 20. Right? The last one in this chart has x minus 2 squared. And what some kids do wrong is they try to distribute that outer exponent, but it's really x minus 2 times x minus 2 minus 6 equals 0. So I need to, again, double distribute. That gives me x squared minus 2x. Now I need to distribute this negative 2, so it's minus 2x plus 4, because a negative 2 times negative 2 is a positive. And then minus 6 equals 0, so I'm going to combine these like terms here, and that gives me x squared minus 4x minus 2 equals 0. It's in standard form. My values of a are 1, b is negative 4, and c is negative 2. Now let's look at quadratics in table form and how we can identify them. With linear functions, we would just find our rate of change. We found our change in y over our change in x. Let's see if we can notice any sort of pattern here. As I go down the x's, it's going up by just 1. What's happening with the y's? Well, subtracted 14, then 4, then it's adding 6, adding 16, adding 26. So just by that, I know for sure it's not linear because I don't have a constant rate of change. But look at what happens if I take my second difference. So this was the first difference in the y's. Now the second difference, it would be adding 10, adding 10, adding 10, adding 10. The second difference is the same, indicating that I have a quadratic relationship. So observe it in this second example. So the first difference, subtract 5, 9 minus 5 gives me 4, then I subtract 3, then I subtract 1, then I add 1, add 3, add 5. Now, no relationship there, but the second difference is 2. It is adding 2 onto each of these, and since the second difference is constant, it's the same, it's indicating it's quadratic. I also just want to illustrate, this one it's easy to see, the symmetrical relationship. You see how 0, 0 that I'm highlighting must be the vertex, and then it goes 1, and then it goes 4, and then it goes 9. So it's got this nice symmetrical relationship, but you're not always going to see that. So now I'm told to create my own table of values and show that it displays a quadratic relationship. So I'm just going to pick something that I know is quadratic to develop my table. So I'm going to do, let's see, is this crooked? Sorry, hold on one second. So I know that y equals x squared plus 3. Okay, it's got a squared term, so I know it's quadratic. So I do an x and a y. I'm just going to pick a few values, like 1, 2, 3, 4, just some consecutive ones, and then I'm going to plug that in. So 1 squared is 1, plus 3 is 4, 2 squared is 4, plus 3 is 7, 3 squared is 9, plus 3 is 12, 4 squared is 16, plus 3 is 19. And now I'm going to illustrate. Okay, so I'm going to look at my first difference here. So this is going up by 3, up by 5, up by 7. My second difference going up by 2, and it's constant, so I'm illustrating that I do have this quadratic relationship. We are going to be doing so much work with quadratic functions this unit, so if you are struggling to change anything to standard form or recognizing what makes it quadratic, please reach out to me early and get some help.